Somewhere beneath the city where you live, there is a bridge, or a tunnel, or a highway overpass. It was built within your lifetime, or perhaps within your parents' lifetime. Engineers designed it. Governments paid for it. Workers poured thousands of tons of concrete to hold it together, and already, right now, it is dying. Hairline fractures creep through its steel-reinforced bones. Water seeps inside. Rust blooms in the rebar like a slow disease. In 50 years, maybe 70 if the winters are mild, that structure will be condemned, torn down, rebuilt, and your taxes will pay for the replacement, just as they paid for the original. Now consider a building in the center of Rome. It was completed around the year 125 AD. It has survived 19 centuries of earthquakes, floods, barbarian sacks, medieval neglect, Renaissance plunder, 2 world wars, and the daily vibration of modern traffic. Its dome, spanning 143 feet from edge to edge, remains the largest unreinforced concrete dome ever built on Earth. No steel, no rebar, no polymer additives. Nothing but Roman concrete, volcanic ash, and an engineering instinct so precise that modern scientists needed electron microscopes and particle accelerators to begin understanding how it works. That building is the Pantheon. And the material holding it together is not merely surviving, it is getting stronger. This is not poetry, this is chemistry. And the fact that a civilization which collapsed 16 centuries ago produced a building material superior to anything manufactured by the 21st century is not just an architectural curiosity. It is a question that should unsettle every engineer alive. This is the story of how Rome discovered a secret hidden inside a volcano, built an empire on top of it, and then lost the recipe when the empire fell. A recipe we have spent decades and millions of dollars trying and failing to recover. The answer begins not in Rome, but in the ground beneath a fishing village on the Bay of Naples, in a landscape shaped by fire. The Italian peninsula is, geologically speaking, a violent place. It sits on the collision line between the African and Eurasian tectonic plates, a zone of relentless seismic pressure that has produced some of the most famous volcanic eruptions in recorded history. The western coast, in particular, is studded with volcanic fields. Vesuvius dominates the skyline south of Naples. The Campi Flegrei, or Phlegraean fields, simmer just to the west, a supervolcano whose caldera stretches 7 miles across and whose last major eruption, roughly 39,000 years ago, blanketed the entire eastern Mediterranean in ash. It is this ash that matters. Over millennia, eruptions deposited vast beds of volcanic tuff and fine powder across the region. A gritty, calcium-rich sediment the Romans would later call pulvis Putiolanus, the dust of Puteoli, after the port town of Puteoli, modern Pozzuoli, where it was most abundantly harvested. Today, geologists call it pozzolana. It looks unremarkable, gray-brown, powdery. If you scooped a handful from the hillside, you would not guess that it contained one of the most consequential chemical properties in the history of construction. Mixed with lime and seawater, pozzolanic ash triggers a reaction that produces a calcium-aluminum silicate hydrate crystal structure, a molecular lattice that not only binds aggregate into solid mass, as all concrete does, but continues to grow and reinforce itself over centuries as moisture penetrates the material. No other civilization on Earth had access to this specific geology in such abundance, at such proximity to a rising imperial power. The Egyptians had limestone, the Greeks had marble, the Mesopotamians had clay. Rome had a volcano. But the Romans did not discover this material through science. They discovered it the way most ancient peoples discovered transformative resources, through proximity, accident, and the slow accumulation of trial and error. The earliest known uses of volcanic ash as a binding agent in construction date to roughly the 3rd century BC in the towns and farmsteads of Campania, the fertile coastal region surrounding Vesuvius. Farmers and local builders noticed that when volcanic ash was mixed with quickite lime and rubble, the resulting paste set harder than sun-dried mud brick and, unlike gypsum-based mortars, did not dissolve when exposed to water. In a coastal region battered by storms and tides, this was no minor advantage. Structures built with the mixture outlasted everything around them. Word traveled north, to Rome. At the time, Rome was not yet an empire. It was a republic, aggressive, expanding, but architecturally modest. Roman buildings of the 4th and 3rd centuries BC were constructed largely from tufa blocks, timber, and basic lime mortar, methods inherited from the Etruscans and Greeks. The city's ambitions were growing faster than its infrastructure could support. The Senate needed roads to move legions. Generals needed ports to supply campaigns. Administrators needed aqueducts to sustain a population that, by the 2nd century BC, would exceed 500,000, enormous by ancient standards, comparable to medieval Paris 1,500 years later. Tufa and timber could not meet this demand. They cracked, rotted, and burned. The solution arrived from the south. Roman engineers, likely military engineers attached to campaigns in Campania, began experimenting with pozzolanic ash mixtures sometime around 300 BC. The material they developed was called opus cementitium, from cementum meaning rough-cut stone or rubble. It was not poured like modern concrete. It was layered by hand, a bed of mortar, then a layer of fist-sized stones or broken pottery, then more mortar, then more rubble, built up in courses like a lasagna of rock andite paste. The process was labor-intensive, but the result was extraordinary. Once cured, opus cementitium was waterproof, fireproof, and strong enough to bear immense compressive loads. It could be molded into any shape. It could be poured underwater. And it required no highly skilled stonemasons, only laborers, rubble, ash, and lime. This was the critical advantage. Stone construction demanded expert craftsmen who could cut, transport, and fit heavy blocks with precision. Concrete demanded volume. Rome had an almost unlimited supply of both labor and volcanic ash. The engineering historian Lynn Lancaster has estimated that by the height of the empire, Roman concrete construction consumed tens of thousands of tons of pozzolana per year, transported by ship from the quarries near Puteoli to building sites across the Mediterranean. The supply chain itself was an industrial achievement, barges loaded with grey volcanic dust crossing the Tyrrhenian Sea in fleets, feeding a construction appetite that no previous civilization had imagined. The first great proof of concept was infrastructure, not architecture. Roads, harbours, aqueducts. The Aqua Marcia, completed in 144 BC, carried fresh water to Rome from springs over 56 miles away, its channel lined with hydraulic concrete that sealed against leakage with a reliability that would not be matched until the cast-iron pipes of the 19th century. The harbour at Puteoli itself was rebuilt, using concrete poured directly into wooden forms submerged in the sea. The first known application of underwater concrete construction, a technique so effective that sections of the harbour floor remain intact today, harder than they were when first laid, 2,000 years of salt water having only strengthened the crystalline bonds within. But it was in the capital itself that concrete would reveal its true potential. As the Republic gave way to empire, Rome entered an age of monumental construction driven by political ambition, public spectacle, and the personal egos of emperors who understood that buildings were a form of propaganda more durable than any speech or decree. The man who understood this first, and most completely, was not an emperor at all. He was Marcus Vipsanius Agrippa, soldier, admiral, statesman, and the closest friend of Augustus Caesar. Agrippa was Rome's supreme pragmatist, a man who preferred results to credit. He financed and oversaw the construction of Rome's first great public baths, its improved sewer system, and several new aqueducts. But his most consequential project was a temple he built in the Campus Martius around 27 BC. A rectangular structure dedicated to all the gods, which he named the Pantheon, from the Greek Pantheon, meaning all divine. Agrippa's original Pantheon burned in a fire in 80 AD and was struck by lightning and burned again under Trajan. What stands today is not his building, but the one that replaced it, the Pantheon, as rebuilt by Emperor Hadrian, completed around 125 AD. And it is Hadrian's Pantheon that contains the engineering miracle. Hadrian was not a typical emperor. Where his predecessor Trajan had been a conqueror, Hadrian was a consolidator, a man who pulled legions back from overextended frontiers, toured every province of the empire on foot, and involved himself obsessively in architecture and design. Ancient sources suggest he personally contributed to the plans for his greatest projects, sometimes clashing with professional architects. The historian Cassius Dio records that Hadrian once quarreled bitterly with Apollodorus of Damascus, the most celebrated architect of the age, over a design disagreement. Apollodorus dismissed Hadrian's ideas. Hadrian later had him exiled and, according to some accounts, executed. Whether this story is precisely true or inflated by later gossip, it captures something real about the emperor. He cared about buildings the way other rulers cared about battles. The Pantheon was his masterpiece. From the outside, it presents a conventional Roman temple facade, 8 massive Corinthian columns supporting a triangular pediment with Agrippa's original dedicatory inscription still carved across the lintel. But step through the bronze doors, and the interior reveals something that no visitor in 125 AD had ever experienced, and that no architect since has replicated without steel reinforcement. The dome, a perfect hemisphere of concrete spanning 143 feet, rising to a height of 143 feet, so that a perfect sphere could be inscribed within the interior space. At its apex, a circular opening called the oculus, 27 feet across, open to the sky, the building's only source of light, casting a beam that moves across the coffered ceiling like a slow sundial as the earth rotates. When it rains, water falls through the oculus and drains through almost imperceptible channels cut into the slightly convex floor. The engineering behind this dome is a study in controlled paranoia. Roman engineers knew that concrete was strong in compression, but weak in tension. It could bear weight pressed down upon it, but would crack if pulled apart. A dome this size, if built uniformly, would generate enormous outward thrust at its base, enough to push the walls apart and collapse the structure. To counter this, the builders varied the density of the concrete itself. The lower sections of the dome contain heavy aggregate, dense volcanic tuff and travertine. As the dome rises, the aggregate shifts to lighter materials, pumice, and then, near the oculus, nothing but pure pozzolanic morite paste with air pockets. The dome literally becomes lighter as it ascends, reducing the load at the point of greatest structural vulnerability. The coffered ceiling panels, which appear decorative, are in fact structural. Each coffer removes weight from the dome while maintaining its curved geometry. The walls at the base are 21 feet thick, roughly the width of a 2-lane road, tapering to less than 5 feet at the crown. Imagine the day the formwork was removed. For months, perhaps more than a year, the interior had been filled with a massive timber scaffold, a forest of beams and arches supporting the wet concrete as it cured. Workers had climbed this scaffold daily, hauling buckets of mortar and aggregate to be packed into the curving form, layer by layer, ring by ring, each course slightly thinner and lighter than the last. No one alive had ever attempted a span this wide without columns. No mathematical model existed to guarantee it would hold. The decision to remove the formwork was, ultimately, an act of faith backed by experience. The timber was pulled away. The dome held. 1900 years later, it still holds. There is a second figure whose contribution to this story is quieter, but arguably more lasting than either Agrippa or Hadrian. His name was Marcus Vitruvius Pollio, and he was a military engineer who served under Julius Caesar before retiring to write the only surviving architectural treatise from the ancient world, De Architectura. 10 books covering everything from city planning to water systems to the properties of building materials. In Book 2, Vitruvius describes the preparation of lime, the sourcing of pozzolanic ash, and the precise ratios of aggregate to morite that produce the strongest hydraulic concrete. He writes that the best ash comes from the region around Puteoli, and that when mixed with lime and rubble, it produces a mass that, as he put it, becomes as hard as stone, especially when used in water. He recommends specific proportions: 3 parts volcanic ash to 1 part lime for marine structures, and warns against using river sand, which lacks the chemical reactivity of volcanic material. Vitruvius was not a great architect. His prose is technical, sometimes tedious, and his buildings, as far as we know, were competent but unremarkable. Yet his text became the most influential construction manual in Western history, copied by medieval monks, rediscovered by Renaissance humanists, studied by Brunelleschi, Michelangelo, and Palladio, and printed in more than 80 editions between the 15th and 18th centuries. Without Vitruvius, much of what we know about Roman concrete would have been lost entirely. He was not the genius who invented the dome. He was the clerk who wrote down the recipe. And the recipe worked on a scale that defies modern comparison. At its territorial peak, around 117 AD under Trajan, the Roman Empire encompassed roughly 93 million square miles, an area larger than the European Union today. Across this territory, Roman engineers poured concrete to build roads stretching over 250,000 miles, aqueducts delivering 300 million gallons of water daily to cities across 3 continents, harbors from Caesarea on the Levantine coast to Leptis Magna on the Libyan shore, bathhouses large enough to hold 3 Siwauzaran bathers at once, and amphitheaters like the Colosseum, whose concrete foundations have supported 50,000 spectators and nearly 2 millennia of earthquakes without critical failure. The port of Caesarea Maritima, built by Herod the Great with Roman engineering expertise around 25 BC, offers perhaps the most astonishing example of concrete's durability in hostile conditions. To create an artificial harbor on a coastline with no natural bay, engineers constructed massive concrete blocks underwater by lowering wooden forms into the sea and filling them with pozzolanic mortar mixed with seawater. The blocks, some weighing hundreds of tons, were laid on the sandy seabed to form breakwaters. 20 centuries of Mediterranean currents, storms, and biological encrustation have not destroyed them. Marine archaeologists studying the submerged remains in the 2000s found that the concrete had developed an aluminous tobermorite crystal structure, a mineral so rare and so strong that modern materials scientists struggle to reproduce it in laboratories. The seawater that should have corroded the material had instead catalyzed a chemical reaction that made it harder and more resilient with each passing century. This was the paradox that haunted modern engineers. Roman concrete does not merely resist decay. It feeds on the forces that destroy modern concrete. Moisture, which rusts rebar and cracks Portland cement, triggers crystal growth in Roman pozzolanic mixtures. Seawater, which eats modern marine structures from the inside out, provides the ions that fuel the formation of aluminous tobermorite and philipsite within Roman harbour walls. Time itself, the universal enemy of all human construction, is Roman concrete's ally. But no material, however strong, can protect a civilization from itself. By the 3rd century AD, the empire that had poured concrete across 3 continents was fracturing from within. The crisis of the 3rd century, from roughly 235 to 284 AD, saw more than 20 emperors rise and fall in 50 years, an average reign of less than 30 months, most ending in assassination. Civil wars consumed legions that should have guarded frontiers. Inflation gutted the currency. The silver content of the denarius, once nearly pure, was diluted to less than 5%, turning Roman coins into copper tokens plated with a memory of silver. Trade networks contracted. Provincial cities that had once imported pozzolana from Puteoli by the shipload could no longer afford the freight. And beyond the frontiers, pressure mounted. Germanic tribes, Goths, Vandals, Alemanni, Franks, pushed against the Rhine and Danube borders with increasing frequency and force, driven partly by their own population growth, partly by climatic shifts that made the northern steppes less habitable, and partly by the visible weakness of an empire that could no longer garrison its own walls. In 260 AD, Emperor Valerian was captured by the Sasanian Persian king Shapur the Fum, the first Roman emperor ever taken prisoner by a foreign enemy. According to some accounts, Shapur used Valerian as a human footstool when mounting his horse, and after the emperor's death, had his skin stuffed and displayed in a Persian temple. Whether or not the story is entirely true, it captures the psychological shock of the moment. Rome was no longer invincible. Diocletian's reforms at the end of the 3rd century stabilized the empire temporarily, splitting administrative control between East and West and establishing a new capital at Nicomedia. Constantine would go further, founding Constantinople in 330 AD as the new seat of Roman power in the East. But these were survival measures, not solutions. The western half of the empire continued to erode. Britain was abandoned in 410. Gaul and Hispania fragmented into patchworks of Roman authority and barbarian settlement. The Vandals crossed into North Africa in 429, severing Rome's grain supply from the breadbasket provinces. And on the night of August 24th, 410, an army of Visigoths under King Alaric breached the walls of Rome itself and sacked the Eternal City for the first time in 800 years. The physical structures survived. The Pantheon stood, the Colosseum stood, the aqueducts stood. What collapsed was not the concrete, but the system, the administrative machinery, the trade networks, the training pipelines, the institutional memory that told a master builder in Gaul how to source pozzolana from Campania, how to calcine limestone at the correct temperature, how to proportion the mix for underwater work versus load-bearing walls. Concrete is a recipe. And recipes live not in buildings, but in minds, in hands, in the daily practice of skilled workers passing knowledge to apprentices across generations. When the Western Empire fell in 476 AD, the last emperor, a teenager named Romulus Augustulus, a name that reads like bitter irony, combining the founder of Rome with the diminutive Little Augustus, was deposed by the Germanic chieftain Odoacer and sent into quiet retirement on a villa in Campania. The date is symbolic more than decisive. The empire did not collapse in a single dramatic moment. It faded, province by province, generation by generation, like a language losing speakers until one day no one alive can pronounce its words. And that is precisely what happened to Opus Caementicium. No invader banned its use. No decree outlawed its formula. The knowledge simply thinned. Fewer builders knew the correct ratios. Fewer ships carried pozzolana. Fewer patrons could afford monumental construction. Medieval builders in Italy sometimes reused Roman concrete as quarry material, breaking apart ancient walls to harvest the aggregate for new, cruder construction. A civilization cannibalizing the bones of its predecessor without understanding the chemistry that had made those bones indestructible. By the 12th century, the art of hydraulic concrete construction in Europe was essentially dead. When medieval cathedral builders needed waterproof foundations, they reverted to techniques the Romans would have considered primitive: rammed earth, timber piles, basic lime mortar that dissolved in groundwater within decades. The rediscovery was slow and incomplete. Renaissance architects read Vitruvius carefully, but understood his recipes imperfectly, lacking both the specific volcanic ash he described and the empirical tradition that had refined its use over 5 centuries of Roman practice. In 1756, the British engineer John Smeaton, tasked with building a lighthouse on the wave-battered Eddystone rocks off the coast of Plymouth, experimented with lime and clay mixtures and independently rediscovered that certain calcined limestones, when mixed with volcanic-type materials, produced a hydraulic cement that set under water. His work led, indirectly, to the development of Portland cement in the 1820s by Joseph Aspdin, the material that would become the foundation of all modern concrete construction. Portland cement is, by any measure, a triumph of industrial chemistry. It is cheap, versatile, and mass-producible. It has built the modern world. Every skyscraper, every freeway, every dam, every airport runway on the planet rests on some form of Portland cement concrete. Global production exceeds 4 billion tons per year. Humanity uses more concrete by weight than any other manufactured material on Earth. But Portland cement concrete has a fatal flaw. It cracks. Microfractures appear within years of pouring, caused by thermal expansion, chemical shrinkage, and mechanical stress. Water infiltrates these cracks, corroding the steel reinforcement that gives modern concrete its tensile strength. The corrosion expands, widening the cracks, admitting more water, accelerating the cycle. The average lifespan of a modern reinforced concrete structure is 50 to 100 years. The American Society of Civil Engineers has estimated that the United States alone faces a backlog of over $2 trillion in infrastructure repair, much of it related to deteriorating concrete. Roman concrete does not crack this way. Or rather, when it does crack, it heals itself. In 2023, a team led by Admir Masic at the Massachusetts Institute of Technology published a study that overturned decades of assumptions about Roman concrete. Scientists had long noticed small white chunks of calcium carbonate scattered through Roman concrete samples, fragments called lime clasts. Previous researchers had dismissed these as imperfections, evidence of sloppy mixing or incompletely slaked lime. Masic's team demonstrated the opposite. The lime clasts were not mistakes. They were the mechanism. Roman builders, the study argued, did not fully slake their lime before mixing, a process called hot mixing. They deliberately incorporated chunks of calcium oxide, quicklime, into the wet concrete. When the concrete later cracked and water seeped in, the water reacted with these embedded lime clasts, dissolving them and precipitating fresh calcium carbonate, essentially filling the crack with new mineral growth from inside. The concrete was not passively enduring. It was actively repairing itself, using the same moisture that destroys modern concrete as a trigger for regeneration. The lime clasts functioned as chemical reservoirs, waiting dormant for the crack that would activate them. The irony is almost unbearable. For decades, modern analysts had looked at the lime clasts and seen flaws, evidence of an imprecise, pre-industrial process that lacked the quality control of modern cement production. What they were actually seeing was a self-healing technology so elegant that it required 21st century instrumentation to recognize. The Roman builders may not have understood the chemistry in molecular terms. They did not know the word tobermerite. They could not have drawn the crystal lattice of calcium aluminum silicate hydrate. But they knew, through centuries of empirical practice, that concrete mixed with hot lime and volcanic ash from Puteoli outlasted everything else. They knew it, the way a grandmother knows that bread rises better on a warm day, not through theory, but through the accumulated, undocumented wisdom of 10,000 repetitions. Today, every 60 minutes of your life still contains 60 minutes. Every circle you measure still contains 360 degrees. These are Babylonian inheritances. But the concrete beneath your feet, the sidewalk, the bridge, the basement wall, belongs to a younger and less durable tradition. It is Portland cement, born in the 19th century, and it is already dying. Somewhere in Rome, the Pantheon stands open to the sky, rain falling through its oculus onto a floor that has drained it perfectly for 19 centuries. The dome above does not lean, the walls do not bow, the concrete does not crumble. It is older than every cathedral in Europe, older than every surviving castle, older than the English language itself. And inside its crystalline lattice, at a scale invisible to the naked eye, minerals are still growing, still bonding, still strengthening. A chemical reaction that began when a Roman laborer packed volcanic ash and quicklime into a wooden form in the reign of Hadrian, and that has not yet finished. We build for decades, they built for millennia. And the secret was not genius. It was not divine inspiration. It was grey dust from a hillside near a volcano, mixed with fire and seawater by hands that understood what their minds could not yet name. The next time you drive across a bridge and see the cracks in its guardrails, the rust stains bleeding from its joints, the orange cones marking another round of eternal repair, remember that 2,000 years ago, someone solved this problem. They solved it so completely that their solution outlasted their language, their government, their gods, and their name. And we, with all our science, all our polymers, all our computer models and electron microscopes, are still trying to read the recipe they left behind in stone.